Ooh, ah. All right, good morning, ladies and gentlemen. Time for rotational review. Do you know your circle parts?
Gots to know the players to play the gang.
And before, there's a lot of slides here that we're going to go over. The challenge here is, can you go find these in your notes already?
Yeah.
Okay. All right, so we've got a circle, we've got our radius, our diameter, the center of our circle, and this is a line tangent to the circle. Circumference is going to be the whole way around.
Yeah, and the important thing about the tangent is it's perpendicular to the radius at that point.
Yes. The distance traveled for the object moving once around a circle is 2 pi r, because that is the equation for a circle.
That's
right?
the circumference, yeah.
The circumference of a circle. The time required for one lap is called the period.
Time for one lap.
Seconds for one cycle. Speed equals distance over time. The speed of an object in circular motion is distance over time, so 2 pi r over t. Okay, so it's the speed of an object in circular motion. As you were twirling the stopper, if you guys remember me doing that.
And we got a stopper right here.
Yeah, oh, we do. Great. Grabbed it. Okay, so as we're twirling the stopper, I'm gonna go ahead and just go like this, okay? As we're twirling the stopper, what is happening? What's happening to its velocity?
Well, its speed looks like it's about the same, but what's the difference between speed and velocity?
Well, one of them has direction, right? So if I stop this right here, I'm actually gonna pretend like it's going this way, right? So if I stop this right here, at each point,
Oh, the
Okay.
direction of the velocity is constantly changing.
right, okay? So as you were twirling the stopper, the direction of the velocity is constantly changing. Is this an acceleration?
Yes, it is.
The answer is yes, okay? Instantaneous velocity is the speed and direction at a point in time. So like we just said, right here.
And if you twirl the stopper and let go of the string, that goes off in a direction, tangent.
to wherever I let it go.
Yeah.
I was like, do I have anything breakable over there? No, just the wall. Okay. So, boom, there we go. Okay, instantaneous velocity, speed and direction at a point in time. The direction of the velocity is constantly changing. That makes it an acceleration.
Because
Right?
acceleration is the rate of change of velocity.
Over time. Okay, Newton's first law of motion states that an object in motion will continue in a straight line path unless acted by an outside force. Now, the direction of the net force causing this acceleration is toward the center, right? Okay, as I twirl this around in a circle,
Yeah,
what's keeping it from just going in a straight line path like when I just
It's
let it
the
go?
string.
The string. And the string, the direction of the net force, so as we go this way, velocity is this way, but my net force is pointing in towards the center. And we have a lovely, oh, go ahead.
Centripetal has the word center in it.
Yeah, it's like a little thing. And so then we have our equation here.
This is Newton's second law
Mm-hmm.
for things going around a circle.
So our centripetal force is equal to mass times centripetal acceleration. And we have an equation for centripetal acceleration, which I think we're going to be getting to soon.
Yeah.
The acceleration is always the same, is always in the same direction as the net force towards the center. That makes sense, right?
Centripetal force, centripetal acceleration.
Yeah, because they're equal, right?
Yeah.
Same direction. Okay, so if I asked you what direction, if I stop going around a circle, what direction was the force and what direction the acceleration, your answer should be towards.
Yeah, it's
the center.
you think that, well, gosh, it's constantly changing. That makes it hard to say, but it is really a simple solution that's just toward the center.
And here is our equation for centripetal acceleration.
Yep. V squared over R.
V squared over R. If work equals force times the cosine theta delta D, does the centripetal force do work?
Well, force and the instantaneous change in position from one instant to the next is always tangent. So what's the angle between the force and the displacement?
It's 90 right here.
And what's the cosine of 90 degrees?
Cosine of 90 is 0.
That's right.
So the answer is no. It does not do any work. The centripetal force does not do any work. So what does this say about the potential energy of a satellite in circulation? Well, if there's no change in, if there's no work being done, there's no change in energy, right?
It's not going higher or lower. It's just staying at the same altitude. The potential energy doesn't change.
No change in the potential energy. Okay. I was like, are you doing that? I don't know. Okay. And on to torque. Torque is a twisting force.
It's when we held the book in our hand out at arm's length.
Mm-hmm.
Yeah.
Hold it. Let me do it. No.
Yeah, well, that's.
I got one right here for you. I guess I can put mine in there. Right?
And we asked you to do this at home. If you hold it down at your side, doesn't hurt. But then as you bring it out, and stop right there, ouch, and then keep going up, doesn't hurt as much.
Not as much.
Okay, because what's happening is it's applying a twisting force to your shoulder.
In what direction is the force this whole time, Boykin?
Well, gravity is always down.
Okay.
So gravity is always down, and so you're, well, we'll get to the why that works here. We talked about it before.
Yeah. So is that the next slide?
Well, you had the axis of rotation.
Did I just, oh, right here. Okay.
Okay. It's one of the important players.
Oh, sorry. Yeah, I accidentally hit this thing. So our axis of rotation, that's the.
That was your shoulder.
Yeah, right here. Okay. The line of action. Okay, so the line of action is extended line drawn collinear with the force. So when we had our book, right, at this point, the force of gravity is down.
It's always going to be down, and so if you draw a line down from the book and up from the book, that's the line of action.
Collinear. And I was like, Mr. Morgan, what does that mean again? Well, linear's line, co is width, so it's just in the same line. What did you say? It's in the same line as it?
It's on the same line, yeah.
Yeah, it's parallel with it or whatever. In this case, it's exact same. It's in the exact same spot.
Yeah.
Okay, so lever arm. So we talked about the axis of rotation, the line of action, and now here's our third player, the lever arm.
No, that's not her arm. The lever arm is the distance between the line of action and the axis on a line that's perpendicular to both.
Okay, so let's take a look at this picture first. So we've got our axis of rotation here, right?
Yeah.
And in this case, someone's exerting a force that direction.
In that
right here.
direction, yeah.
And so our line of action is right here.
Yeah.
And so our lever arm has to be perpendicular to both. So I'm going to go ahead and draw my line right here. So perpendicular right there.
Yeah, and we had a thing where we had a plumb bob that we were holding.
Oh, yeah.
That went, well, you can use this instead. This will do the same thing.
Yeah, okay, so
So
how
if
do
you
we
hold
go
that-
this, Boykin, like this, right?
Yeah, and so,
There we go, like that.
all right, so there's the line of action is that, and you can see that, well, go back up to perpendicular, I know it hurts. Okay, so there the line of action is perpendicular to her arm. So her arm is a lever arm. However, as you go down, it's not perpendicular anymore. In fact, the lever arm is going to be this long. Well, actually, you draw it up here, it'd be toward her shoulder. It'd be that long. And then take it down a little
Maybe right
more.
here, right?
Yeah. Actually, take it up. Take it up.
Yes, sir.
Up, higher, higher, higher. And so now you can see the lever arm is from the shoulder to right here. It gets shorter, and if you keep going up, the lever arm gets shorter and shorter and shorter, and then you take it down.
Oh, okay, now
I
done.
guess it gets longer and longer and longer
More
until
torque.
the maximum, and that's the Alloy point. And then if you keep on going down, you have to extend that line of action up.
Yeah, that's a great visual. Okay. Woohoo! All right. Let's see. Line of action, extended line drawn collinear with the force. Yes, yes, yes. Lever arm is the distance between the line of action and the axis on a line perpendicular to both.
Now, what I would suggest instead of writing this stuff down now is you should be following along in your notes from where you had this before.
You've seen this before. I think I just closed something over there. All right, the torque is equal to the force times lever arm. So this is our mathematical representation
Yeah.
for this.
And so when she was holding the book, the force of gravity was always the same.
Oh.
But as she went around that axis of rotation, the lever arm got shorter and longer as she went up and down.
And so I experienced the most torque, that was
Yeah.
pain, when
at 90 degrees.
because the lever arm was the longest.
That's
there.
right.
How does the equal arm balance find the mass of an object? It was
Well, I should have
clear.
grabbed that. Hey, boys and girls, let's go back to the cabinet. This area off limits to students. Stay away. There we go.
Okay, so Our equal arm balance here, it's just a balance. It just has to do with torques, right? And so what we have is a lever arm over here and a lever arm over here.
So you put something right here, and there's a torque around the center of rotation right there.
This is our axis, and this isn't gonna do it.
No,
But
well, you put masses, and we talked about this when we did it. You put masses over here, and when it's balanced, that means the torque in this direction is balanced by the torque in that direction.
they're equal to each other.
That's right.
Right? Okay, so how does this one go? Find the mass of an object. It has to do with the balancing of torques around that axis.
Yes, ma'am.
Okay, a rigid body can be visualized as a large number of points. So on this ruler, there's a point here, here.
That's right.
Okay. So there are two types of motion for a rigid body, such as this.
Yeah.
We have translational, which if I move it.
Yeah.
Okay. And we've got rotational. So when I'm spinning it, and visualize what's happening to those points as I move them. Well, they all move up here, they all move over here, and as I twirl it, they're all moving.
So in translational, all the points move parallel,
Yes.
and in rotation, oh, there you go.
Yeah. Translational motion, all the points move parallel and parallel paths, whereas in rotational motion, they all move in circular paths with a common center point.
That's right.
Okay. Equilibrium occurs when all external forces and torques sum to zero. That's kind of like what we saw in the balance.
With
right?
the balance,
Yeah,
yeah.
it's the same idea. So, equilibrium. Now, when are things in equilibrium? That is, there's no translational or angular acceleration if it's just chilling there,
That's right.
right? Torques can twist clockwise. Okay, clockwise. This way is negative, or counterclockwise. Counterclockwise this way, which is positive.
Yep.
In equilibrium, torques cancel each other out, positive and negative.
Make zero.
So right there. Okay. Torque two-step. Oh yeah, this one with the diving board, right?
Yeah.
Okay, so for a rigid objects in equilibrium and two unknowns, we have to do a system of equations. And so there's two steps. You need to look at this in two ways. The first is translational.
I think we should draw the diving board.
I think we should too. That's a good idea. And hopefully you already see this. You have this somewhere in your notes, right? And so it's secured,
There's a post on one end.
right here.
Yeah, attached to the ground.
And this one's free to move, and there's a person right here, right?
Well, then you've got the fulcrum. You've got the pivot point right there. You know the.
Oh, where
Yeah.
the two are.
Yeah, and then you
into
got
the
the
ground.
person out on the very end of the diving board.
Like that. Okay. All right. So step one for translational. Let's go ahead and take a look at this. So
If it's just sitting there,
if it's just sitting here, there's no acceleration, which means all of the torques and all the forces are balanced here.
yep, the ups cancel out the downs, the lefts cancel out the rights.
Okay. So let's see, which ones are ups and downs here?
Well, it's like you can use the meter
guy
stick
right here.
to demonstrate that.
Okay. So if I let go right here,
This is a down
Okay.
on this end.
so that's going to be a down. Okay. And then that's going to be an up.
Well, this has to push down, otherwise it's turns.
Oh, right. And then this is pushing up,
That's right.
right? Okay. So we're going to we'll say equal down like this, and this one is going to be 2 times the size like that.
Yep.
Right? Okay. So step one. So this is going to be, I'll just say the force left. This will be the force right. And I'll just call this the force middle. I don't know. I'm running out of fun.
Yep, so the force right plus the force left equals the force middle. They have to cancel each other out. And you might want to put negative sign in front of the force middle.
I was gonna say, did we do absolute value before? I think that's what we did.
Sure.
I can't
Sure.
remember.
Well, negative does the same thing because
yeah.
the right and the left are down,
Yeah.
the middle is up, and so in order to make the middle the same as the downs, you have to put a negative out front.
Yeah. Okay, so that would be step one, translational. And as we would look at this, we would choose one to be our point of axis. So if you wanted to solve for right here,
Yeah.
Okay, then we would just solve for this.
Well, we'll get to that when we get to the torques.
Torques, okay.
See, this
So-
is just translation.
So step one, translational, the x-axis is equal, the net force is 0, the y-axis net force is 0. Okay. So step two is for the net torque. So now we have to think about it rotationally. And of course,
Yeah.
our net forces are equal to 0.
And that's what you were doing over here when you were choosing your axis of rotation.
Yeah,
And
so
you could choose any of them, actually.
it doesn't really matter.
Yeah.
I'll choose the left, so that means that we're gonna go, we'll say negative, what was that?
Well, if you choose the left as the axis of rotation,
Oh, the
then you've
negative.
got two torques.
Yeah.
There's the torque due to the middle that's counterclockwise, and you got the torque due to the right that's clockwise. So you've got two torques here.
Okay, yes, so I'm gonna go ahead and draw on the board with them.
Yeah, sure.
Okay, so the first thing I do is I need to solve this equation for
And
the
since it's in
variable.
equilibrium, it's 0.
Yes. So I'm gonna go ahead and solve this equation for our right here. So I'm gonna say negative force.
Okay, no, you want to do torques here.
Well, but for the first part, don't I need, when I solve for my torque, I have to be able to plug it in here, right? So for my rotation.
You're getting ahead of yourself. Just put the net torque
Okay.
is equal to the torque due to the middle
Yeah.
plus the torque due to the right equals 0.
Yeah, which equals 0. Okay, and then I can go ahead and subtract one of these on this side.
Well, we're not, you're getting ahead of yourself. We
Yeah.
just need to know this on the bottom and number 1 and number 2. We'll get to that other stuff eventually.
Okay, so our next step here, so solve a step for one variable and insert it into the other step to solve for the other variable. Okay, so that's what you're saying right here. Okay, so we have to solve this step for the,
Well, let's say we know the force on the right.
okay. So
Let's
what
say the
is-
force on the right is 10 newtons, and the length there is the lever arm from the left.
from the axis,
Yeah, from the axis. Let's say the lever arm is 10 meters.
10 meters.
And
Okay.
let's say that the lever arm for the middle is, what does that look like? Say 4 meters. 4 meters. So we know the force on the right, we know the lever arm, we know the lever arm for the middle, but we don't know the force on the right. So you would solve this in your torques down here. You'd have force times the lever arm,
So we'd say, do you want
Yeah,
me to
just-
write it in there?
just
Okay, so
force times the
force up on the right times the lever arm on the right. Okay, like that.
plus the force in the middle.
Times the lever arm in the middle.
Yeah.
And now this is the only thing we don't know, right? Because we know this.
Yeah, make that an F. Force in the middle.
Oh, shoot, right there.
Yeah.
Okay. So if we wanted to solve for this, so that's
Well, what you're
be
going to have is they'll add up to 0. Both
Yeah.
of those add up to 0. So that means -1 on the left is equal to the -1, +1 in the middle.
Yeah. So we've got this is equal to the torque on the right, like this.
Yep.
Right. And so then you've got the negative force on the middle times the lever arm in the middle equals the force on the right times the lever arm on the right. Now we can divide by the lever arm in the middle, divide by the lever arm in the middle,
Boom.
and we know that the force is going to be, let's go and plug them in here. So this was the force on the right, so that's 10 newtons, right?
Yep.
Okay, times the 10 meters
Yeah.
divided by 4 meters. So that's 100 divided by 4. That's going to be 25,
Sure.
right? So that'd be 25 newtons. Negative. Okay, so that's the force in the middle. Now, what do we do with that, Boykin?
Well, let's see. Now, so we know the force in the middle. We know the force on the right. What's the force on the left?
Okay, well,
See, we don't know the force on the left.
we don't know the force on the left, but we know the force on the right. So if we just look at our picture up here,
Yeah.
we can really easily see it, right? It's really obvious that this is going to be 15 newtons. Yes.
You got 10 newtons down and 25 newtons up. What plus 10 is 25?
Yeah, and if you really need to like see the math for that, you've got, now this is the part that I always kind of like get a little confused about, is when I see like a negative and a negative here, I'm like, okay, wait, hold on, what's going on? Now, this is why the drawing is super helpful.
Yeah,
right?
diagrams will save you.
The diagram's gonna save you, because I see this here and I'm like, okay, so really it's gonna be like negative 25. Let me just play around with this, like this, Boykin, 10 newtons, is that minus 10?
Well, and
Oh,
negative.
plus positive, and there's our 15 right there. Do you see it?
Yeah.
There we go. Sorry, that's how I do my math. To do my math. So you plug it in here. I had a negative here because.
Well, no, you can't. It is a negative, and it stays a negative in front of the 25. So that's negative 25 minus 10 is. Let's see, negative 25.
No, but I have a negative.
Oh no, you're
here,
right. No, you're right.
With that negative in there.
Sorry.
See, and this is why it's so important, because it's like, okay. So what are the things that this is a fun problem to do. So what did we do here again, Boykin? The first thing that we did was we solved for
The translational.
the translational, right?
I think it gives you the steps there in the next.
Right there.
Yes. First, find all the forces on the right going to the right, cancel out the forces going to the left. All the forces in the up equals the forces in the down.
Okay, and then we essentially came up with this equation right here, because our net torque is equal to 0, right?
Yep.
Okay, so from here, that is when we did this, the net torque is equal to 0. We solved for one of the variables up here, and again, we just chose this as our axis rotation. We could choose a different.
You could choose the middle one if you wanted.
Yeah, you could choose the middle one, and then you're just gonna set these two equal. This would be the left one instead of the middle one. Okay, and you just solve from there. Okay. Whew, it's been a while. All right. So linear and circular motion are parallel universes. Okay, changing gears here a little bit. Let's talk about how the kinematics here are the same, or similar, if you will. A number line has a 0 point, and every point has a position, x, measured from it.
To the right is positive, to the left is negative.
Okay, linear displacement is the change of position.
The final minus the original.
Always. Okay. The unit circle has a 0 point, and angles are measured from it.
That looks like a pie.
Lovely. Okay. Angles can be measured in degrees or radians. Our lovely friend, the radians. So 360 degrees is equal to 2 pi radians, right? 360 degrees is equal to 2 pi radians.
I only see one pi there. Sorry.
This is one. And then let's go ahead and do a little conversion thing. Well, actually, they should be able to do this.
Yeah.
Okay, so 1 degree is how many radians? 1 radian is how many degrees? Look in your notes, find this.
So you need a fraction for the first one that has degrees on the bottom and radians on the top. And for the second one, you need a fraction that's flipped over that has radians on the bottom and degrees on the top.
Radians, degrees, radians. Okay.
Yep.
The arc length, S, traced by a position, depends on the radius and the angle. Okay, so I'm reminding myself of when we went like this, right?
Yeah.
We covered the moon.
Right.
Right? And this little guy, this was our S, right? That was our S right there, the
Arc
length of
length.
my arc length, my length of my thumb.
The width of your thumb, yeah.
This was my radius, and my angle is from here to there.
Right.
Right? Okay, so then we have our Rosetta Stone, so important. S equals R theta. You need this in order to go from the linear world. I don't know why I'm using my mouse. That's what I do in Zoom. Because the Zoom people can't see me talk. The linear world to the
Angular world.
angular world. Thank you. Okay.
It's like this. Well, go ahead. Let's go on to
keep going.
displacement.
Okay, angular displacement. That looks just like linear displacement, but with a different variable, yes?
Yeah, it's like here on this, if we have this that goes from here to there, that's going about, what is that, 90 degrees from here to here?
I'd say so.
You could say the displacement from here to here is 90 degrees, or however many radians that is.
You could convert.
Or you can say from here to there, that would be 2 pi radians. The displacement would be 2 pi radians.
Yes.
And it would be the same for every one of these dots. As this one goes quarter turn, so does that one. So does that one. Each one of them all are having the same angular displacement, even though they might travel different distances.
Okay. Angular displacement is a vector quantity. Like the unit circle, counterclockwise is positive. One revolution equals 360 degrees, which equals 2 pi radians. We're just adding in that one revolution, right?
Yeah, an interesting thing about this turntable, this is 33 revolutions per minute.
Ooh.
This is 45 revolutions per minute.
Ah.
So you could convert those into radians per minute or degrees per minute. And that would be an angular velocity. Well, we're not there yet, sorry.
Linear velocity is the rate of change of position, right? Meters per second?
Yeah.
Okay, so it only makes sense that angular velocity, which is represented by our omega here, is radians per second. Just like how this is distance and time, it's going to be radians per second.
Yeah, let's, if you don't mind, let's go back over here, turn this thing on. Okay, now this is going in the negative direction, I notice.
Because
And
right?
even though which one is going fastest, the one on the outside covers more, has a longer S, and this one has a shorter S, they all have the same angular velocity. They all have the same number of radians per second or revolutions per minute. They all have the same angular velocity.
Boom. Okay. I like that, Boykin. Okay, the directional component of omega is along the axis of rotation, determined by the right-hand rule.
We're not going to make a big deal out of this, but if this was turning in this direction, the right-hand rule says the direction of the vector would be up and out.
We didn't spend that much time on that in class either. Linear acceleration is the rate of change of velocity. Okay, we know this. So it would make sense if angular acceleration is the rate of change of angular velocity.
Yeah, that's like it's like this. The original velocity is 0. On your mark, set, go. It takes a certain amount of time to get up to its angular. Well, no, it gets up to speed very fast. It's up to speed. So it goes in a certain time interval from its original velocity up to the final velocity.
That 33, right?
Yeah.
Okay, so we could calculate angular velocity. In fact, I think we did.
We did all this stuff before.
The direction of the acceleration depends on whether the omega is increasing or decreasing. So if you have something that's increasing speed, going from 0 or whatever to 33 revolutions per minute, or whatever radians per second.
Yeah, it's like when you turn it on or when you turn it off. Here the acceleration is one way.
And
Here the acceleration's in another way.
Yeah. That's a way better example than just words trying to explain it. Inertia is an object's resistance to change. Remember inertia? In its motion. Okay. Mass is a measure of inertia.
As Bill Nye says, inertia is a property of matter.
Yeah, and everyone just memorizes that. I'm like, what does that actually mean? The moment of inertia that resists rotation is determined by the distribution of mass inside of the object. Can you guys find in your notes where we had that race where we had a ramp and then we had two
discs.
And one was a solid disc and the other had those ball bearings.
It was a
inside.
ring.
Yeah, it was more of a ring, right?
Yeah.
And so thinking about how those two objects, how their moment of inertias were different, how that affected how fast they moved.
Yeah.
Down that ramp. So the moment of inertia varies with mass and distance from an axis of rotation.
Yeah, it's like the meter stick. If you hold the meter stick in the middle and twist it, it's relatively easy. If you hold it out on the end,
ow, tough.
It's harder. That's because it has a larger moment of inertia. You have a lot of mass, a far distance from the center of rotation.
Yes, this one has a greater moment of inertia. Okay, so how could we rewrite Newton's second law to apply angular motion?
Well, for angular stuff, it's not force, it's what?
It's torque, right?
Yep.
Okay, and then for mass, we just talked about how it's a moment of inertia, and acceleration is just angular acceleration.
Yep.
Okay, and so this is how we could write Newton's second law to apply to angular motion right here. Okay.
Yeah.
which gear should you have the chain on if you are riding a bike uphill?
The little bitty gear or the big gear? Which, for the same amount of force that you put on the chain, will produce the greater torque?
Okay.
You got to draw on the lever arm, I think.
Like that, right?
So if the force is the same, what's that equation for torque? It was.
Torque equals the force times the lever arm, right?
Yep.
Okay, and you're saying if this is the same, right?
So
Which
a
one's gonna
longer, so a longer lever arm is a greater torque.
So you want this one then?
Yep. So you want to get into that big gear if you're going uphill, unless you know you're a
Unless you're one of those
professional.
people who likes to stay on the ground.
Yeah.
Stay in the saddle. That might be me. I don't know. It depends. Okay, depends how I'm doing. Okay, so net torque is equal to the moment of inertia times the angular acceleration. We just saw this.
Yep.
Okay. If momentum, I almost said moment of inertia. If momentum is the moment P equals m times v, and the symbol for angular momentum is L, then we have this equation. Momentum P equals mass, which is moment of inertia times
Velocity.
which is our angular velocity.
Yep.
Oh, it's right there. Boom. Okay. Right. The direction of angular momentum is the same as the direction for angular velocity, which makes sense.
Yep.
Right. Impulse changes momentum. Impulse changes momentum. We have our linear world, which is force times the change in time, mass times the change in velocity. How is this Newton's second law?
Well, force is mass times acceleration.
What if I move this, divide it over here, v over t, that's acceleration,
That's
right?
acceleration.
Okay, so there it is. So can you do this question? How much momentum does a 1,500 kilogram car going 20 meters per second have? You could probably do that in your head.
Okay, that's 2 times 15 is 30 plus 3 zeros. That'd be 30,000 kilograms meters per second.
Okay, I'm gonna write that down. 30,000 kilograms meters per second, right? Okay, now I want to know what impulse is required to stop it.
Well,
Does an impulse change momentum?
yeah, so it'd be equal to the change of momentum, yes.
So it's equal to that, right?
Except in the negative direction.
In the negative direction, I apologize.
Yeah.
Okay, required to stop it. Thank you. Okay.
Yeah.
So if it comes to a stop in 4 seconds, what is the average force exerted?
Well, let's see, force times time is impulse. So it's 4 seconds. That'd be 30,000 divided by 4 is 15. That'd be 7,500 newtons.
30,000 to stop it, right?
Yeah.
So then the time is 4 seconds.
4 seconds. So
Do it. Plug it in.
yeah, it's
Whatever that is,
7,500 negative 7,500 newtons. You got to push in the opposite direction to slow it down.
Okay, that's making sense. All right. And here are the string of equations that we just, sort of used here.
Yeah.
Okay. We've got the impulse. We've got impulse momentum theorem. We've got momentum, right? And then the
And so what we're
parallel
doing here
universe.
is we're showing the 2 parallel universes, like you said. Yeah.
Boop, 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 boop. Nice color coordination. Okay, we're almost done. All right, so we've got a 10 kilogram pulley of radius 0.5 meters is connected to a 5 kilogram mass. What can we know?
Well, if we assume that the pulley is like a disc, we could find the moment of inertia.
Okay.
So we can find the moment of inertia. Let's see here. Let's see if I can find that moment of inertia. Impulse and momentum, rotational dynamics. It's going to be 200 something.
210, I think. I remember seeing it on there. On the board. It's a solid cylinder, right?
Yeah.
Not 210?
No. Lever
We're
arm,
close.
center of gravity.
There it is.
Here it is. So if yeah, you had it right. It was
Whatever.
1/2 mr squared. If it's a solid sin, so we could get 1/2 m. So we could get the
Oh, right here.
moment of inertia.
I was like, where do I write this? 1/2 mr squared. Okay, so you guys see how we can get that right? Our radius is what, 0.5 meters?
Yeah. And we could find the force of gravity that's acting on the thing,
That's going to be
50
50 newtons. Okay, which means
and we could find
we could find what else?
the
Force-
torque, because
force of
the
tension.
radius is going to be the lever arm. Yes, just like this right here.
Okay. Oh, yeah. So the torque, right? The torque is the force times the lever arm,
Yeah.
right? And the force is going to be the force of gravity or the force of tension, right?
It'd be 50 times 0.5. That's going to be 25 Newton meters.
Meters. Now, I had to take a second to kind of axis is here, the force, our axis of rotation is here. Do we have a place that's going to be perpendicular to our axis of rotation?
That's the tangent right there, tangent to the
so
radius.
this is our lever, of course, which happens to be the radius.
Yeah.
Okay. Boom. Starting from rest, the mass drops for 2.5 seconds. What is the angular moment?
Okay, and we're going to stop right here
Yeah.
because there's actually a lot more going on, because as it starts to fall, the tension changes. If you remember when we did the over the falls lab.
Oh yeah.
So we're not going to do this, but if we want it, the delta L is equal to the change in momentum. We need to know what the angular momentum at the start is going to be 0.
It's this, right? Mass times velocity, right?
Yeah.
Right?
Well, it's going to be at times the change of the angular velocity.
Oh yeah. There we
Yeah,
go. Which is
just
going
like
to be
that.
final minus initial. And at the beginning, it's going to be 0 radians per second, right?
Yeah, and we're not going to do this.
Okay, you could figure that out, but like we said. Okay, and I think this might be, what is it? And there it is, find the angular velocity. Okay,
Yeah.
do that. And then what is the angular acceleration? You could also do that, but we're not going to. Okay, because you got the time and you got the velocity at that point.
Yeah.
Conservation of angular momentum. The total momentum of a closed isolated system is constant. The total momentum in the beginning is equal to the total momentum in at
That's
the
a
end.
prime. It didn't
Yeah.
show up very well.
And that's it.
Boom, boom, boom.
So we just went over a lot of stuff. Did you find it in your notes? Relook over stuff.
All right.